Hello, my name's Scott Barry. I'm a biostatistician with Barry Consultants. I'm going to talk to you today about a very simple statistical idea. I think it's taken for granted by many statisticians and really not very well understood in the sports world and the drug development world. So I'm going to parallel the implications of this very simple statistical technique and claim that it costs billions of dollars, the lack of understanding of this. It can have an enormous change. So I will parallel the sports world and drug development world of a very simple idea. So let me start by giving you two questions. And I'll show you the parallel of these two questions and why they're really in many ways the same question. Jose Altuve for the Houston Astros last year led the major leagues in hitting, batted .341, meaning he had 225 successes in 660 trials for a 34.1% success rate. The question is, how good is he? What is his probability of getting a hit? If he were to play that season over again, what do you think he would hit? Is your best estimate of that 341? Oncotherion is a drug company, and they ran a phase 2 trial, and they saw the hazard ratio for overall survival in stage 3B LR patients was 0.524. That was the hazard ratio. What is the estimate of the hazard ratio for running phase 3? Two simple questions. I'll explain why these are not as simple as they seem. So this goes all the way back to a bet I made when I was 10 years old with my father. In 1977, I was a big baseball fan, and George Foster of my favorite team, the Cincinnati Reds, had 31 home runs halfway through the season. I was sophisticated enough as a 10-year-old that I could double, and believe that if you take any player, on average, what they do the first season is what they'll do the rest of the season. I could double 31 home runs. It was 62. The record at the time was 61 by Roger Maris, so I figured he's got at least a 50-50 chance of breaking the record. So I bet my dad, and he was extremely generous and said that I can even have 54 and larger. He'll give me anything 54 and larger, and that was the bet. He ended up hitting 52, and I lost the bet. This was not the only bet I lost. I lost a number of these. Eric Dickerson, in 1983 as a rookie, had 995 yards halfway through the season, and he had come on very strong after not getting as many carries the first couple games. I could project that forward. It looked like he was going to break O.J. Simpson's record of 2003 at 2003 yards, and I bet, and again, he ended up 1808. This happened over and over and over again, these bets and doubling. And on average, we expect it to double. Why do these people that were on pace for records, why do they not get there? Is there an effect to this? What is the reason? Why does this always happen? We understand 2 times the first half is a total or projections forward. On average, that's going to be your best estimator of a player. You will, on average, do well. Why do these players who are on pace for a record does this not hold? And many things are talked about. Roger Maris, for example, when he was chasing the record, that he lost his hair. The media scrutiny day after day after day. Sports psychologists, announcers will give you all kinds of reasons why this happens. Is that the reason? We create reasons for this. Is it no more than random variation? And why is it, if it's random variation, does this specifically happen to those on pace for records? So let's work our way up to this. If you look at how Jose Altuve's statistics on ESPN.com, you'll notice they give you over 90 splits for him. They give you on turf, on grass, during the day, during the night, at night on turf, every possible batter's count against every team he played against, all kinds of situations. Over 90 of them, they give you batting averages. What does this mean, and how is this related to the questions I asked you? So they gave 93 splits. 20 of these were each of the individual teams that Jose Altuve played against. So if you look at this, you can see against the Phillies, he batted 200, meaning he had a 20% success rate against the Phillies. Against the Marlins, he batted .538, 7 for 13, 538, and everybody in between that. What does this mean? What does it mean about the Marlins? What does it mean about the Phillies? Would you act as though he's a 200 hitter against the Phillies? Would you bench him for another player who's a 250 hitter against the Phillies? A 300 hitter? Would you walk him if you're the Marlins manager? Would you behave in a way as though he's different against any one of those? Are these different? What I did is I took all of the at-bats and I assumed he was a 341 hitter and I simulated a season. And then I did it again and again and again. And I simulated 10,000 seasons of Jose Altuve as though he's a 341 hitter in every at-bat against every team. He is 341. Then I recorded the worst average he had against the 20 teams and the best average. That's the column with the simulation values. So that on average, his worst batting average against any team was 158. On average, his best was 536. And if you look through down the order statistics of what he averaged against each team, it's almost identical to what he did last year in 2014. It's almost exactly what he did. His numbers against the team mirror what he should have done if he was 341 against every single team. Very reasonable to assume he's 341 against every team, it just doesn't matter. But yet if you investigate 538 by itself, you isolate it from all the other numbers, it looks amazing. And then we act as though it's amazing, and we approach the problem ignoring the other information of what he did. We behave poorly, we pay him too much money, and we act inappropriately, costing us money. All right, we're working up to understanding how these things all come together. So separated, 538 and 200 are unlikely. Individually, they're very unlikely, so we get concerned. This is exactly what happens in drug development. We run a clinical trial, and we see strange things in subsets, and we get very nervous about them. Newspapers report this causes cancer, this cures cancer, you should do this, you shouldn't do that. 5 years later, we hear that we made a mistake and we spent an enormous amount of time and effort chasing these things that turn out not to be real. Can we identify when they may not be real? Here's a nice little cartoon showing this, that a scientist investigate, a PK/PD specialist says jelly beans are related to cancer. So we go ahead and we ask clinical trialists to investigate this. Meanwhile, they're busy playing Minecraft, as you can see in the cartoon. So they go out and investigate it, and it's not just jelly beans, but perhaps the color of jelly beans matters. So they go out and they run 20 trials. They look at red jelly beans, pink jelly beans, mauve jelly beans. It turns out green jelly beans have a p-value less than 0.05. 19 other ones have no benefit. The newspaper doesn't tell you that 19 didn't have an effect. It tells you that green is related, 95% confidence, p.05, and we get all concerned about that. When in fact, you know that if we do 20 things that don't work, on average, one of them jumps up. And we get very concerned. It's taken out of context of what happened. And this is a huge issue in drug development. It's a huge issue in sports. We split everything. All right. Bill James, who is a famous sports statistician, developed many of the analytics and the sabermetrics that are used today, had the following quote, that BS has tremendous advantages over knowledge. Bullshit can be created as needed on demand, without limit, without anything that happens, you can make up an explanation for why it happens. All of you that work in drug development know this is true. We run clinical trials. We can come up with a reason why green matters and no other color matters. We can come up with a reason why Jose Altuve bats 538 against the Marlins. It happens all the time, and we believe it, and we believe in those things, and they're nothing but made up stories. He quotes a story, and you can read the quote, where he watches a KU football game, and it's 7-3. After the first quarter, and they're playing, he says, a Texas team. I think it was the University of Texas. 7-3. Texas goes on to destroy them, scoring 24 points, and they win 38-17. The announcers talk about how it's a road game. It takes the first quarter to get into into the speed of the game, and once they got into it, they knew exactly what they were up against, and they won handily. Of course, had it been reversed and they played great early, and Kansas would have learned what was happening, finally caught up to the Texas team. We can create an explanation for anything, even though it's nothing but randomness. It's true in baseball, it's true of clinical trials. And Bill James understands it and has a filter for the BS. Do we in clinical trials? So Oncotherion have a treatment for cancer. Here is the publication reference for their phase 2 trial. And the greatest effect they observed in stage 3B local regional patients. The median survival time had not yet been reached in the drug arm, but in the control arm it was 13.3 months. A p-value of 0.069, almost significant, but a hazard ratio of 0.524. An amazing effect. If this were true, it would be a blockbuster drug. Surely we can run a phase 3 trial and be successful, 0.524. We can power it, be successful. What is not necessarily talked about here is, why are we looking at that? Is this phase 2 trial one of many trials with similar drug mechanism? Is this subset one of many? Maybe we're not surprised, and this is Jose Altuve against the Marlins. The phase 2 results this was a subset. They pulled it out of a subset. They looked at a number of groups. This is Jose Altuve against the Marlins. So in that context where something has been pulled out separate, we think differently about it. We think differently about that than other subsets, but do we believe 524? Do we believe the hazard ratio is that, or do we believe it's much less than that? More closer to 1. Same thing as the Jose Altuve. They all work together. So this is, we were asked to predict the likelihood of success of this phase 3 trial. We had to try to estimate what is the hazard ratio. Many other firms projected the probability of success in this phase 3 trial to be greater than 95%. And it's hard not to say that looking at the 524. So let's move forward and let's look at what's happening here. This is a scenario, this is a simulation of data where the truth is a 50% success rate. And I'm flipping a coin that has a 50% success rate over and over and over again. And the red is the histogram. The red is the data. That's what you see in the world of drug development, in the world of sports. You see the data. You don't know the truth. You don't know the truth of that drug. You don't know the truth of Jose Altuve. We see the data. We're trying to make inference about the blue. If I knew the blue, I'd run the right phase 3 trial. Or not run not run phase 3. I would pay Jose Altuve appropriately. I would make my decisions in the game appropriately. I need to know the blue. All I see are the data. So this is a natural random variation of a 50% success rate with 50 trials, 50 observations, at bats, 50 patients. You see the blue. Now, the subjects way out to the right, the observations that are near 0.65, the observations near 0.35, the truth of that is 0.5. It was random variation that pushed it out there. Now, what happens in true applications like sports, like drug development, where there is heterogeneity? Not every coin being flipped has the same probability. Here's a situation where I simulate a unit that has a different probability, and you can see that distribution. A mean of 0.5 and a standard deviation of 0.05. Some of them are really good. Some are, in truth, are 0.65, 0.6. Some are 0.4. Now, when you do that and you simulate data, you see the data is much more spread out than the truth of the units. When we look at data and see an observation in the tail, we have to know that variability pushes that out, and it's more likely they're not that good. They're probably closer into the middle. That's the way variability works. It only pushes things out. So when you see things out, you have to recognize that it probably came from something not that far. That there wasn't anything acting upon those individual data points to the left, to the right, other than variability. It's just the truth was more towards the middle. Here's a situation where maybe we have a bimodal distribution. You can see the data doesn't look all that different. And we have to try to, as scientists, as sports fans, as drug developers, figure out what's the truth of the unit underlying it. There's a very, very simple statistical way to do this. You can put all of these on top of each other and see that the red don't look all that different. When you remove the truth about the blue, yes, you see longer tails. You see things more than just random variation from a single unit. And in the bottom, you can tell that something completely dispersed is happening from the data if you get ample data. Here's 100 observations in each case. It's incredibly difficult to tell random variation with heterogeneity from without to huge variability. The bottom one looks quite a bit different. You could probably tell in that case. Our goal here is what blue unit simulated that observation that's near the tail. Who is it we focus on when they're looking for a record? Those that have very extreme values. And so what truth created that blue? Almost surely it wasn't that extreme. It was probably a 0.55 that simulated that if we were to simulate the rest of the season, he behaves like a 0.55, not because of pressure, not because of some dreamed up effect of a commentator, but because in fact he wasn't that good and it was just randomness that put him in the tail in the first place. So how do we estimate what blue created that? The simple statistical idea, hierarchical modeling. Here's a Bayesian approach to hierarchical modeling. We can model the variability in the red as a function of the blue. Here's a binomial model where theta is the blue unit. That's what we want to know. And that's the probability of success for every single unit. The thetas, we model it as a distribution. We recognize the heterogeneity and we model it as a distribution. It has parameters that we model a third level down, this hierarchical modeling. There are red data, there's blue truths, and then there's a distribution of the blue driven by the green parameters. So what happens when we do that? Let's go to Jose Altuve. This is every batting average from 2014. I restricted it to 75 or more at bats. Typical of an everyday player is 500 or more. So there's a few part-time players, a few pitchers that we're going to pull out of the batting here just to show you the distribution. You can see Jose Altuve. There's one person that didn't qualify for the batting average that has a higher batting average, but wasn't as many as you need to win the batting title. He's way out in the tail, 341. We created the hierarchical model that I just showed you, where the bottom level has independent exponential priors. What you see in the graph here is the posterior mean value for each of the blue units. And you can compare from red down to blue the data to the hierarchical estimate. And it does exactly what we need it to do, is to recognize data goes outward and it learns from the population, and the estimate of each player is regressed to the middle of the distribution. Jose Altuve is not believed to be a 341 hitter. I'll talk more about that, as why we think that and why it comes out. You can go to Stein estimation. That is a theorem that this is going to do better than looking at the individual point. The statistical ramifications and consequences are easy and well understood, but in practice we don't do this. The mean for alpha and beta of this distribution is 55 and 163. If you're familiar with this, what this means is before a player takes a swing in a season, you estimate that they have 55 successes and 163 failures. And then you add successes and failures to each one of those to give the estimate, which gives you an estimate pulled in towards 252. Now, as they gather data, it can overwhelm the population and you eventually estimate them to be there, but you need the data to do that. For the Tiger Woods, for the Wayne Gretzky, of course, for every one of those, we see data like them early on from hundreds of people that are not that good. But you eventually figure out Tiger Woods, Wayne Gretzky, Babe Ruth, these guys are different, but it takes the data to get you there. So here's what you would estimate. The x-axis here is the observed batting average in 2014. The y-axis is our estimate of their true probability of getting a hit. If I were to create exactly the same value, this is the line y equals x, where I estimate their batting average should be whatever it was observed. You can see Jose Altuve in the upper right-hand corner. His batting average is 341 and his estimate is 341. Every player does that. The green line was the average batting average across the league of 252. I could use that as an estimate. I could say Jose Altuve is a 252 hitter. The data tells us it's incredibly unlikely. So what is the hierarchical model estimate? It's a weighted average of those as a function of the variance of players and the strength of the data. The size of the dot is proportional to the square root of the number of at-bats for each player. You can see Jose Altuve had one of the more number of at-bats, one of the larger at-bats in the season. And so his estimate is closer to the batting average, the Y equals X line, than the 252 line. Those with much smaller sample sizes, the smaller dots, are pulled into the 252 more, and you get this spreading out of our estimate. So Jose Altuve comes out with an estimate about 320, that we believe he was 320 and he was fortunate, and if he played the season over again, he'd hit 320, is our estimate of that. We could pay him as though that's as good as he is. You don't pay him as a 341 hitter. Okay. I learned this after I lost these bets. I played this card game, Stratomatic Baseball, where you roll dice to replay baseball games. This is Mark McGwire's 1987 card, and you roll a colored six-sided die and then two six-sides and add them up. So for example, a roll of 1-5 you can see is a home run. They make these cards reflect exactly what a player did in the season. They reflect the red and not the blue. So I would replay seasons, did it many times, and I saw records that have never been set in baseball ever before. McGwire hit a 5-home run game in a replayed thing. I saw batting averages, strikeout totals that I've never seen before in simulated seasons. And I didn't understand it until I learned that the red isn't the truth. It's spread out. You assume that's true. You get more spread out data in the next season, and you see things that you've never seen before. And if you took those and simulated more, you'd see more and more extreme values. It's not true because the red is not true, the blue is true. The estimate of the truth captures the variability and not our estimate of the truth. All right, what are the implications? The implications are that we see this over and over again in drug development. We see it over and over again in sports. People believe to some extent that that was true. When it doesn't happen and it's not repeated, we create myths for why that happened, and then we act as though the myths are true. We lose money, we do poor behavior, we make bad decisions. It's nothing but regression to the mean. Nothing but regression to the mean. Here's an example, very simple example. There's for years has been called the Sports Illustrated jinx, that whomever shows up on the cover of Sports Illustrated, things don't go as well after that happens. It's explained by regression to the mean. Who do you put on Sports Illustrated covers? People in the tails. Either they're on the very bad side or the very good side. When they come into the middle, it's nothing but regression to the mean. Who goes to see a golf professional? People who are playing poorly. They start to play better. Wow, that golf pro is amazing. Pay him more money. We take chicken soup when we don't feel as well. We feel better. Why is it? The placebo effect in clinical trials, we enroll patients who by their nature, they're not doing well. You don't enter a clinical trial if things are going well. You enter when you feel bad, your blood pressure's high, you've had too many migraines lately, whatever it is, you enter the trial and lo and behold, you give them nothing and they do better. It's not because of some mystical thought that the placebo helped me. They would have done better if you'd have done nothing to them. They regress to the mean. But yet we create an effect for it. We pay people differently. We pay sports psychologists so that I don't get this regression effect when it's nothing but regression to the mean. It explains partly subsetting from phase 2, running phase 3. We have 15 straight phase 3 Alzheimer's trials that have failed. $500 million one company spent and eventually stopped development. There's a lot of money paid, a lot of misunderstanding of the regression effect. So oncotherion, we were asked to predict. We used a hierarchical model. We modeled specifically the various subgroups. We modeled the history of this disease. It's very difficult to treat. We have hundreds of drugs that have tried and have failed to treat this. We have many phase 2 trials. Our estimate of the hazard ratio is about 0.9, not 0.524. It's the same as Jose Altuve, and thus our predicted probability of success in the phase 3 trial was 40%, not 99% that everybody else estimated. The results of the phase 3 trial came about, were reported. Oncotherion lost 42% of the value of the company in a minute when the results were there. The projection was success, the thought was success, the market misunderstood, people who invested misunderstood, a lot of money was lost, and much of it is explained to the regression effect. So in sports, there's an incredible amount of information that comes from the population which something is drawn from. If you isolate the individual and look at it, it looks strange, but shrinkage in the population is absolutely critical. We fire coaches, we hire coaches, we pay free agents incredibly poorly because of a misunderstanding of this idea. We take strategy decisions that misunderstand this idea. In drug development, we run phase 2 trials. We take at face value the observations that are in the extreme. We plan phase 3, and they fail at incredibly high rates. $100 million phase 3 trials fail after that. And I mentioned Alzheimer's, 0 for 15 in phase 3 trials. These are at least $100 million trials. And it's a lack of understanding of the regression effect. Everybody, when you talk about multiplicities, they all nod their head, yeah, I understand it. And then they go off and they do exactly the same thing that's wrong. I just had a call this morning where a company picked a different endpoint because their effect was a little better. They looked at 12 of them and they picked the best one, and that's fine, but now the belief that you're going to see that again in the next trial is at issue. You underpower trials, they end up failing, lots of money is wasted. So this incredibly simple idea, it's easy to see what happens, it's easy to model. The difficulty is understanding where data comes from, the process of it, putting it together. It's a very simple idea that has to be used. Consumers need to understand it. When you see a newspaper article, ask where it came from. Drug developers need to understand it. Managers and GMs and fans need to understand it. It really is a very simple idea that will completely change your understanding of data. So thank you.